So we are approaching the final line of the discourse. Okay, so this is the last day of the computer architecture course. So and then we will take the final exam on Thursday. Actually, as I announced on the Blackboard, the exam will start 10 a.m. Right? Okay. So there's no conflict, no scheduling conflict. Okay. So the final exam will include what we learned at the midterm exam. Okay, so which means that the final exam will include the pipeline architecture, and the memory hierarchy, and then what we will learn in today's class, which means the parallel processor. Okay, so we briefly cover the parallel processor topics. Okay, so actually the main part of the final exam will cover the pipeline architecture and memory hierarchy. Okay. Okay, so I recorded the lecture video regarding the virtual memory, and then also I hope everyone watched the lecture recorded video. So I will briefly review the virtual memory part. So as I mentioned, the virtual memory. So virtual memory is developed for using the small memory like cache. Okay. So which means actually this is the virtual address, and then this is the physical address. To the software, so which means that actually software access data using virtual address. So which means that if we execute the load instruction like load over A, then this address is the actually virtual address. And but in order to access the real data, so I said that physical means real, and then virtual means it's fake, right? So in order to access the real data, you need to translate this virtual address into the physical address, right? And then we use this page translation. So as I mentioned, we cannot translate the byte by byte translation, right? So for this byte by byte translation, we require large amount of translation selected information. It's not good for the computer system design. So actually, we set the data chunk called the page, and then this chunk size is usually 4 kilobytes. Okay, so which means that for this page, so in order to represent the size of the page, we allocate 12 bits of the address field, and then we just translate the upper part of the address. So upper part of the address is called the virtual page number. So which means that actually we translate the 4 kilobytes of data chunk, the virtual address of the 4 kilobytes of data chunk into the physical address. So actually this virtual page number is translated in the physical page number. And then I explained that in order to translate this virtual page number called the BPM, and it looks like this structure. So we use the data structure called page table. And then I mentioned that this page table is the software data structure, right? So which means that the operating system manages the page table when a processor is launched on the computer system. And then actually it looks like this data structure. So the index is the BPM, the virtual page number, and then when the index is given to the page table, then we can read the physical page number, PPM. Okay, it looks like this. Also, this page table needs some control bit, such as the valid bit, like it's like a cache. So actually, if we can find the valid physical page number from the page table, then we can get the physical address, which is pointing the data in main memory, the physical memory. But if this valid bit is 0, so which means that this virtual page number is pointing the data block on freeze, right? So then this event is called page fault, and the page fault is a kind of exception. So which means that operating system actually provide the exception handler. So page fault handler for is page fault event. So which means that a page fault is detected, then the exception is raised in the processor, and then processor calls the page fault handler. So this is how the page table is used for virtual address to physical address translation. But as I mentioned on the recorded video, no, the page table is the software structure, and then which means that the page table is found in main memory. Okay, so which means that in order to translate the virtual address into physical address, then we need to access the page table for every access. So which means that we need to reference the page table in main memory. So it will take time, it will take cycles. So in order to reduce this performance overhead by a page table accesses, then we can use the TLB. So TLB is actually the cache of the page table. Okay, so TLB is the translation of the first size buffer, and then actually when a page table entry is accessed, then this accessed entry is stored in the TLB, and after that, then we can access the page table using the same virtual page number, right? Because of locality. Okay. So actually, the strong locality is observed in our applications usually, and then actually also the page size is the 4 kilobytes. So which means that when an application is executed, and this application will access the data in the same page again and again, okay, because of locality. So which means that if we just store the one of page table entry here, then we can expect that the access is from our application will access here. So which means that here the hit will be observed in our translation local style buffer, right? So we can think that the TLB is the cache of the page table entry. So in this case, we can use the virtual page number as we can access the TLB using the virtual page number. So, and then as I mentioned, the TLB can be organized like a cache. So which means that we can use the part of the virtual page number as the index of the TLB. Also, we can use the upper part of the virtual page number as the tag of the TLB. So then TLB stores the physical page number, which is mapped by virtual page number, right? So TLB includes some control bit. So, and then so I also explained about the TLB and cache interaction in the recorded video. So actually, in order to access the data, the real data, then we need to get physical address. So which means that before accessing cache, we need to access the TLB. Okay, so which means that we need to get the physical address. But we can organize the cache and TLB in a different way, which means that if the TLB is firstly accessed, then the cycle can be wasted by this TLB accessed. So, and then when I explain about the Aaron cache, actually when we design the Aaron cache, then we focus on reducing peak time for designing Aaron cache, right? So, and then, but if the TLB is firstly accessed, then cycles can be wasted by this TLB access. So, some processors just access the Aaron cache using the virtual address. Okay, sometimes some processes. So we can also select some different approaches for TLB and cache interaction. Okay, that's what we learned in the previous class. Then actually the memory hierarchy includes the two important topics. The first important topic is the memory cache hierarchy, the cache organization. And the second topic is the virtual memory. So as I mentioned, the virtual memory is the mixed part. So which means that the virtual memory is also managed by operating system, and also the virtual this virtual memory management is supported by hardware. So this is very important topic on the computer system. Okay, so I meant the operating system is the mandatory course of the computer in the computer science department. So I hope you can understand the virtual memory. Okay, so so this is the new chapter from this text. Actually, we will briefly cover about the parallel processor architecture. So I believe everyone is familiar with the parallel process architecture. So it means, so actually we frequently say like, oh, my smartphone has the 4 cores, or 8 cores, or even 8 cores, or so we can say, oh, my smartphone processor has the big little architecture. Okay, so it means that the smartphone processor has multi-cores. So what is the core? So actually in chapter 4, we learned about the process architecture. So which means that we learned about the architecture of a single core. So core means the core. Core is some separated processor which can execute thread or some programs. So actually, if we just mention a core, then this core is the independent processor unit. So which means that in the core, then we can execute a thread or a processor. Okay, thread or processor. Then core has also the processor like the ALU and the pipelines. Also, the single core includes the Aaron caches. Okay, Aaron caches, because when we learned about the process architecture, that we learned that this processor includes the instruction memory and data memory. And then I mentioned that these memories are actually Aaron caches, right? Also, the modern processor includes the L2 cache in the core. Okay, so usually the Intel processors, the single core includes the processor, the pipeline like the ALU, the instruction fetch unit, and then register, also some other unit, and then also a single core includes the Aaron cache. That is some complete processor architecture. Also, So Intel Core includes the L2 cache. So if we see the photo die, the photo of Intel Core Intel architecture, then we can find that there are several cores. Okay, like core 1, core 2, core 3, and core 4. And then also we can find the L3 caches. The L3 caches are called the LLC, the last level cache. And then usually L3 cache is shared by multiple cores. So which means that, as I mentioned, the L2 cache is included in the core, but L3 cache is not included. So L3, because the L3 cache is the shared cache. So this is the typical architecture of the modern processors. So which means the modern processor use the multi-core architecture. Okay, then why do you use multi-core architecture? What is the benefit of the multi-core architecture? As I mentioned, a single core can execute a thread, a single thread. And then if we have multiple cores, then which means a single CPU chip can execute multiple threads at the same time. Okay, so there are multiple cores, and then each core can execute the independent thread. So which means with this multi-core architecture, then we can execute the multiple thread, which means that multiple applications usually. So with the multi-core architecture, then we can increase the latency or throughput. Okay, because there are more workers, so which means that we can increase the number of the amount of workload which can be done in the same time. So there are more workers. So that is the benefit of multi-core architecture. So with the multi-core architecture, we can increase the throughput of the CPU across the CPU chip. But we cannot increase the which means that we cannot improve the latency of a single core, a single thread, because only single thread is assigned to this single core. So which means if we have only a single thread, a single thread, then this single thread is assigned to one of these cores, and then other cores are in the idle state. So other cores do nothing. Only this core is working for this single thread. So which means we cannot reduce the execution time of a single thread. Okay. So which means that's why when you mention the multi-core architecture with the multi-core architecture, then we can improve the throughput, not latency, and throughput of a processor. So as I mentioned, then with this multi-core architecture, we can execute multiple threads, and then this parallelism is called the task level or process level parallelism. So parallelism means so we can execute multiple tasks or multiple something using process unit. So as I mentioned, the multi-core architecture can execute the multiple threads at the same time. So this parallelism is called the thread level parallelism. Okay. And then in chapter 4, we learned about the pipeline architecture. Actually, the pipeline architecture also utilize parallelism, but different kind of parallelism. So in the pipeline architecture, this pipeline architecture can execute the multiple instructions at the same time, but in the different stages, right? So, for example, the pipeline architecture can execute in the different stages to execute 5 instructions at the same time, but in the different stages. Okay, so the first instruction is in the write back stage, and then the second instruction is in the memory stage, and third instruction is in the execution stage, right? So, but if we see the time domain for the pipeline architecture, so we can say that in the pipeline architecture, multiple instructions are executed at the same time. And then this kind of parallelism is called the instruction level parallelism. Okay. But with the multi-core architecture, we can utilize the thread level parallelism. So which means with a single chip, we can execute multiple threads. Okay. That is the benefit of the multi-core architecture. So this is the example of the hardware and then software. Okay. So which means that in the serial is a very old CPU. It's a Pentium 4. Pentium 4 has only a single core in the CPU chip. So this is the example of a serial hardware, and then it's a quad core 0. It's also very old CPU because the recently the desktop CPU such as i3, i5 also include the 4 cores. The quad means 4. Okay, so which means in a single chip there are multiple cores. This is the example of a multi-core architecture. And then in the software side, we can classify the software like the sequential execution and then concurrent execution. So this is the example of the sequential execution, the simple matrix multiplication. Okay? So if we write the matrix multiplication kernel, so it's the software, then we can write the kernel as aggressive for sequential execution. But operating system, if you check the number of threads or number of running processes on Windows or Linux operating system, then we can find that many processes or many threads are running on our computer systems. So which means when operating system is working, and operating system launches many threads or many processes, and then these threads or processes are running concurrently. So this is called the concurrent execution. Okay, so example is the operating system. Okay, so but let's think about the parallel programming. So why is this critical? So let us assume that this is a workload. So which means it's a software. So it's a workload for it's a workload. So but this is a quad-core CPU. So which means that this CPU includes the 4 cores. Okay, this quad core, and then we want to improve the performance of this application. Then how can we improve the performance of this application using quad core CPU? How? So as I mentioned, if this application generates only one thread, a single thread, then we cannot improve the performance of this application, right? Because if this application generates only one thread, then this one thread is assigned to one of these 4 cores, and then only this core is used for security is one thread, but there is no benefit if we just use this application, this kind of application. Then how can we improve the performance? If we split, if we divide this application into 4 threads, okay, so multiple threads can be generated from a single application. Okay, if we generate 4 threads from this single application, then we can assign this thread into each core of a CPU. Then we can increase so we can improve the performance of this application, right? So it's the same to our task. So if we can split our task into the multiple parts, then we can assign these multiple parts to the different members, right? So we can improve the performance. Okay, it's the same. It's the same for the CPU architecture. But what are difficult parts of this division of workload? The difficult part is that our task has some dependencies. So some parts is very hard to split. That is the problem, right? So every task cannot be split into multiple parts, okay? Because this task has some dependencies, okay? So that is the difficult part of the parallel programming. So parallel programming means that in a single application, in order to generate the multiple threads, then we can apply the parallel programming technique. Okay, so you are not. I believe you are not familiar with the parallel programming because this is some advanced part of the programming. But in order to exploit this multi-core architecture, then we need to write a code to generate multiple threads. Okay, so actually it's not easy, right? So for example, let's think about the matrix multiplication, like matrix A multiplied by matrix B. Then how can we write the code that can generate multiple threads? Which means that how can you split this workload? So we want, in order to exploit this quad core CPU, then we want to split this matrix into the 4 parts, and then this matrix into also another 4 parts. But it's not easy, right? Actually, for the matrix multiplication, we need to require the entire row, the elements in a single row of this matrix, and then entire elements in a single column of this matrix. Right. It's not easy to split the matrix multiplication funnel. So which means we need to develop parallel algorithm. Is right? So the most of the algorithm is it's not serial algorithm. So which means actually like the matrix multiplication, actually the entire row is multiplied by entire column of these matrices. But in order to develop the parallel application, then we need firstly we need to develop parallel algorithm. That's why the algorithm is very critical. Recently, the algorithm is very critical. It's a very important course in computer science. Okay, firstly, we need to develop the parallel algorithm. But also, even though we develop the parallel algorithm, some tasks cannot be divided. Okay, so which means that this is the workload. Then some part of the workload can be divided into the multiple parts, but some parts cannot be divided, cannot be split. So in this case, we cannot utilize this quad core, the multi-core architectures, because this part is not split. Okay. So this is another difficult part of the parallel programming. Also, in order to generate the final result, then we need to merge the result from a split part. Right. So which means we need so this is some multiple parts, the divided part, but maybe the execution time can be different. It's the same for the real world, because even though there are multiple members, then some members can perform their task, but some members work slowly. So which means that the complete time is can be different. But in order to merge the result for the final result, then we need to wait until this low core complete each execution. Right. And then this issue is called the synchronization. So because of the synchronization issue, and also the performance is not scalable to the number of cores. So scalable means that if we invest the n cores, then we can expect the performance is improved by n times. Why? Because we invest n times of hardware resources. But it's not true. So it's very difficult because of these issues. Like so firstly, we need to develop the parallel algorithm. So this is the algorithm part. But even though we apply the parallel algorithm, the perfect parallel algorithm, some task has some part of the task has cannot be parallelized. Also, there are issues such as the synchronization, and then also the communication, also data dependency. So there are many issues. So and then because of these issues, so we cannot improve the performance of our application like n times. N means the number of cores. Okay, so that is the difficult part of the parallel architecture. So difficulties: partitioning, coordination, and communication overhead. Okay. So let's discuss about the Amdahl's law. So Amdahl's law is also very important law in computer system area or computer architecture area. So actually, this Amdahl's law but it's very simple. It's not difficult. So Amdahl's law tells us that the sequential part can limit speed up. So what does that mean? So actually, so this is the task, and then we want split this task into the multiple thread or multiple tasks to exploit multi-core architecture. But as I mentioned, this task may include the parallelizable part. So parallelizable part means that this task can be split into multiple parts, and then these multiple parts can be executed in parallel. Okay, this is the parallelizable part. But also, this task can include the sequential part. Okay, so which means that so this is the workload, and this workload can be split into the multiple parts, but some part, then this workload cannot be split into the multiple part, it's a sequential part. So actually we can split, we can divide this task into the parallelizable part and then sequential part. Okay, so, and then ideally if we ignore the performance issues such as the communication and then synchronization and some other issues, then simply we can assume that this parallelizable part can be perfectly parallelized by multi-core architecture. So for example, if we have 100 cores or 100 processors, then we can improve the execution time of the parallelizable part as like the T divided by 100. Right. So this is the execution time of the parallelizable part if we apply multi-core architecture. Right. But how about the sequential part? So sequential, we cannot split the sequential part into the multiple parts. So which means that even though we employ parallel architecture or multi-core architecture, we cannot improve the performance of sequential part. Right. So this is the execution time of the time by its 100 processors. Okay, so speed up is the parallelized. So one is the original execution time. Okay, so it is T. But if we apply the multi-core architecture, the parallelizable part is the divided by 100, and then actually the sequential part is the remaining part of the parallelizable part. It's a 1 minus f. Okay, this is the speed up. Actually, the Amdahl's law explains this equation. The speed up is determined by actually the sequential time. Okay, so in this example, as that, so with the 100 processor, and in order to achieve 90 times of speed up with the 100 processor, 100 core, then this problem at the fraction of parallelizable part. Okay, so the fraction of the parallelizable part. So when we calculate the speed up, so this is the baseline machine. Okay, and then this is the execution time by parallel architecture. Okay, so the target is the 90 times of speed up. And if we solve this equation, then fraction of parallelizable part is the 0.999, which means that in order to achieve 90 times of speed up with the 100 core architecture, then in our application, this application has the 99.9% of parallelizable part. So which means that the most of the part need to be parallelized in order to achieve 90% of speed up. So even though we invest 100 cores, so many cores, so we cannot achieve the n times of speed up. Okay, that's what Amdahl's law said us. Okay, which means that actually, even though we apply the parallel processors or parallel architecture, this sequential part can limit the speed up. Okay, that is the Amdahl's law. So this is the example. So workload is composed of a sum of 10 scalars and then 10 by 10 matrix sum. So scalar means that scalar is the sequential computation. Okay. And then, it's the 10 by 10 matrix sum, not multiplication. So we know this matrix sum can be parallelized. Why? Because it's like this. So A, B plus C, D, and then E, F, G, H. And matrix sum is the A plus E, then P plus F, C plus G, like this. So we can perform the element by element addition in parallel for the matrix sum. Then calculate the speed up by 10 core architecture and then 100 core architectures. Okay. How about the single processor execution time? Let us assume that the processor requires 1 clock for this computation. So for the single processor, the execution time is the 10, and then so actually the 10 by 10 matrix includes the 100 elements, right? So which means that the execution time is the 10 plus 100 multiplied by execution time of n. Okay? So 1 clock. And then if we apply the 10 cores, then you cannot improve this part, right? That's what Anders law said, because this is the sequential part, scalar. The sequential part cannot be improved by multi-core architecture. So it's the same, but we can improve only this part, the parallelizable part. So the new execution time for the 10-core architecture is the 20 multiplied by Tn. So what is the speed up? Speed up is the 110 divided by 20 is the 5.5. So in this example, so we just invest the 10 cores, okay? And then what's the expected speed up? So the maximum speed up is the 10 core architecture is the 10, right? Because the 10 is the maximum speed up, but in this example, the speed up is just the 5.5 is the 55% of the potential speed up, the maximum speed up. Okay? It's very low, much lower than the expectation because of this part, 10 scalar. And if you use the 100 processor, the speed up is just 10. It's 10% of the potential. It's much lower than the maximum performance improvement by 100 cores. Because of why? Because of this part. We cannot improve the sequential part within the multi-core architecture. That's what Anders law says. So, but if we increase the size of the matrix at the 100 by 100, then we can easily calculate that the speed up by 10 processor is the 9.9. It's the 99% of potential. And then if we use the 100 processor, it's the 91% of the potential. So what does it mean? Why the speed up is improved with the 100 by 100 matrix? It is because it's part. Her parallelizable part is increased. Okay? So Anders law told us that if we want new multi-core architecture, then we require parallel programs, parallel applications. So which means that our application need to include the large fraction of parallelizable part. That's what Anders law says to us. Okay. Okay. So this is the Amdahl's law. So actually, the Amdahl's law is the also the important law in computer architecture field. And then, okay, let's discuss about the Flynn's taxonomy. So this is called the Flynn taxonomy. So taxonomy means that it's the kind of study regarding classification. So which means that it's the classification of the process of architecture based on the data stream and then instruction stream. So which means that instruction. So which means instruction and data stream means that. So in chapter 2, we learned about the risk by the instructions, right? And then if we see this instruction, then we can say that x1, x2, x3. So in this example, then this instruction, add instruction just handles scalar data like x1, x2, x3. So this register only includes the one element. So this kind of data is called the scalar data. Scalar. Okay. But we can think about some vector type instructions such as the add.b and then b1, b2, b3. So this is the vector type register. So what is the vector? So B1 includes the multiple elements like the elements of E1, E0, E1, E2, and En. And then P2 also includes the multiple elements like F1, F0, F1, and then Fn. And then P3. Then this instruction handles the vector type data, and then vector type data includes the multiple elements. The single vector type data includes the multiple elements. So which means that with a single instruction, like this instruction, handles the multiple data, right? So if we just compare this instruction and this instruction, we can just say that, oh, with a single instruction, then single data stream is handled. Now, into this, and then for the right side instruction, with this single instruction, multiple elements, multiple data streams are handled. Okay, so based on how the instruction handles the data, then we can classify the process of architecture. And then this classification is called the Flynn's taxonomy, based on the data stream and instruction stream. But it's very simple, right? We can classify data streams like the single data stream and the multiple data stream, such as the scalar data and then vector type data. So instruction, the single instruction and multiple instruction. So if we use the single instruction and single data, then this type of processor is called the SISD. So actually, this is the single core CPU, the Intel Pentium 4, it's a very old type CPU. And then SIMD, with the single instruction, then multiple data streams are handled, like the vector type instructions. And then this type of architecture is called the SIMD architecture. It's a single instruction, multiple data. It's called the SIMD. So SSE instruction is actually x86 processor supports the SSE instruction for the multimedia applications. For multimedia applications, the x86 supports the SSE instruction. So which means that it supports the vector type instruction. So say the this architecture is called the SIMD architecture. So MISD, the multiple instruction and single data, so it's not used. So no example. And then MIMD is the multiple instruction and multiple data. It's the multi-core architecture. Intel Xeon, the multi-core architecture. So actually in chapter 4, we learned about this architecture. It's a single instruction and single data. But as you know, actually the smartphone processors also, our desktop processors also run many multimedia applications such as YouTube, game, and then also the music. Actually, many applications are multimedia applications. So which means in order to improve the performance of this type of application, processor supports the SIMD type instructions like SSE. So Intel also includes the SSE instruction. Also the ARM processors, the smartphone processors also include the SIMD type core for the Neon. Okay. Okay. So vector processor supports the vector type instruction, this type of architecture. Okay. This is the example, and this is the example code of the vector type instruction. Okay. Vector type is by code. And so this is the last part of the today's class. So hardware multi-threading. So what is the multi-threading? So I believe you have heard about the hyper-threading of Intel CPU. What is the hyper-threading? So sometimes you can see some Intel specifications such as this CPU has 4 physical cores, but this CPU can run 8 logical. This CPU has the 8 logical cores. What does that mean? Because this Intel CPU supports hyper-threading. What is the physical core and logical core? The 4 physical cores and 8 logical cores. Hyper-threading. So, as I mentioned, the physical means the real. Okay, so which means that this CPU chip includes the really 4 independent cores. Okay, so number of physical cores is the 4. This is the real number of cores. What does that mean? Logical cores. So actually we see the dipole of this Intel CPU. There are 4 cores. Then what does 8 logical? So logical is also similar to the. It's not virtual. It's not fake because it's not fake. But logical means that logically we can run 8 threads concurrently. So I mentioned that a CPU includes the multiple cores like N cores. I mentioned that with the N cores, we can run N threads simultaneously, N threads concurrently, N threads at the same time. Right? That's our expectation. What's logical core? So with the logical core, the 8 logical cores means that with this CPU, we can run 8 threads concurrently. Okay? Because of hyper-threading, Intel hyper-threading technology. So hyper-threading, like this technology means that this technology is the kind of hardware multi-threading. So hardware multi-threading means that with one physical core, this physical core can run multiple threads concurrently. That is the hardware multi-threading. Okay, how? So actually, so if we see the inside of the processor, actually processor has the multiple execution unit. Okay, multiple execution unit for add, multiply, also square, then load, the multiple execution unit. But with this multiple execution unit, the processor only executes the one instruction per thread. Right. So what does that mean? Even though processor has multiple workers, with these multiple workers, we can only execute the one instruction per clock. But because there are multiple workers, this processor has a potential to execute multiple instructions using multiple execution units. So then how can we support the multiple thread? In order to support the multiple thread, then the processor needs to have multiple program counters, the PC1 for the program count 1 for the thread 1, and then program counter 2 for the thread number 2. Also, when the threads are executed concurrently, then we require independent register files. So which means that register files for thread number 1 and then register file 2 for thread number 2. Okay, so which means that so think like this, when an instruction, this file instructions are executed, the instructions access the register file, which is the register file numbers. So in order to execute the multiple threads at the same time, then we need to have a single processor needs to have multiple program counters, then multiple register files. How about the execution unit? Oh, this processor has multiple execution units. So using this multiple execution units, we can run multiple instructions. And then write back, then because already this process has the multiple registers, then we can also write back the result in the multiple separated registers. So what does that mean? A single core processor already has multiple execution units. Okay? It's different from the pipeline architecture we learned. The pipeline architecture we learned has only one ALU, but in a real CPU, a single core has the multiple execution unit. So if we just add the multiple program counters and then multiple register files, then we can run the multiple threads at the same time concurrently. So this technique is called the hardware multi-threading. So multi-threading, so which means that we can execute multiple threads simultaneously concurrently. Okay, it looks like this. So this is the thread A, thread B, and thread C, and thread D. And then let us assume that a processor, a single core can run these 4 threads at the same time. And then there are 3 different kinds of hardware multithreading. It's a coarse-grained multithreading, and then fine-grained multithreading, and then simultaneous multithreading. SMT means the simultaneous multithreading. Okay, so actually this is equal to the hyper-threading of Intel CPU. So The coarse-grained multithreading means that if a thread encounters cache miss, okay, and we learned that if cache miss is encountered, then the thread needs to wait long cycles until the data is fetched from the low-level cache or main memory, right? So if cache miss is encountered, then the processor switch the execution to different thread number B. Then, and then this uh, switch is called the context switch. Context switch. So which means that the thread execution is changed from a certain thread into the different thread. This context switch is it's called the context switch. Okay. So cache miss is encountered, then thread is changed to the thread B. So this is the coarse-grained multithreading. And then fine-grained multithreading means that at every cycle, the thread execution is switching. So which means that at the first cycle, the thread A is executed here. And then second cycle, the thread B is executed. And then the third cycle, the thread C is executed. Okay, so this means the instruction. So this rectangle. Simultaneous multithreading means that instructions can be assigned to the instructions last until, and then the instructions can be assigned from a different thread until the instructions last are filled. So which means in this example, there are 4 instructions last. And then at the first class, the thread A has the 2 instructions. So these 2 instructions last are assigned from a thread A, and then remaining 2 instructions last are assigned from a thread B. In the next cycle, this instruction is assigned to this instructions last. This is the simultaneous multithreading. So multithreading means that with a single physical core, single real core, then this single core can run multiple threads concurrently at the same time. That is the hardware multithreading. So that is so that is the so in this class we learned about some basic concept of this multi-parallel processor architecture, but it's just we just learned about the concept. Okay? Actually, the parallel architecture is really complex, right? So compared to the single core architecture, actually in chapter 4 we learned what very simple pipeline architecture is a single core architecture. But compared to the single core architecture, the parallel architecture, actually when we apply the parallel processor architecture, then we need to consider the very difficult and complex issues. Okay. So actually, if you take some graduate level computer architecture course, then we will cover some advanced issues in the parallel processor architecture. Okay. So this is the end of the chapter 6. So I will conclude this course. So, okay. So that's what we learned. So actually, what is the object of this course? The object of this course is exploring control system architecture and abstraction level. It's an abstract field, so we did not learn about some circuit level or the logic level architecture. We just learned about the control system architecture, the hardware architecture, abstract level, like the microarchitecture or architecture level. So we learned about the basic concept of the computer systems, and then performance, chapter 1, chapter 2, chapter 3, pipelining, chapter 4, and then memory hierarchy, chapter 5. Okay, that's what we learned. So this is the very basic course from the computer architecture field. Okay. So what we did not learn. So actually, modern process architecture is the out of order processor. So actually, in chapter 4, we learned about the pipeline architecture. So it's very, very simple. Okay. And for modern process architecture like the Intel i3, i5, the Intel architecture, or even the smartphone processors have out of order process architectures. Okay. Also, so these topics are advanced topic in computer architecture research, computer architecture study. Okay, so if you take the advanced computer architecture course, then you can learn about these topics. Okay. So this is the first question. So I asked you the first class. The first class of this course. So which process is better? I hope you can answer. Okay, which process is better? Why? G1 and I7. Okay, here. Also, recently, actually, the computer fields are quickly advancing, which means that it change the computer study, like a computer engineering or computer science, so it's changing very quickly. Okay, and then it's also same for the computer architecture. So recently, so we are using the desktop processors or the application processors such as the ARM processors, but so recently, so we also focus on the domain-specific architecture, such as the GPU. So you know the GPUs are widely used for the machine learning or AI application, but this GPU architecture is different from the architecture, CPU architectures. Okay, it's really different. So which means that we just focus on the new architecture. So which means that the traditional concept of the architecture is changing recently. Okay, so that's why recently it is called the golden age for computer architecture. Okay, so if you are interested, then you can watch this Turing Award lecture. It's a very good lecture. I recommend. So after the final exam, then you can watch this video. Okay, so this is my research area. So if you are interested, then you can also apply for the undergraduate research intern. Okay, so this is my contact information. Okay, okay, this is the end of this course. Any question? Any comment? Okay, so, okay. I was very happy to teach you. And then, okay, so we have a final exam. And then, good luck for the final exam. Okay, so thank you very much. Thanks. 감사합니다.
감사합니다.